Math 2414, representing functions as power series. Fifth example, differentiating to create a power series. All right, let's put the previous theorem into action. Recall the following power series, the one that I dubbed a very useful series once upon a time. 1 over 1 minus x equals the sum from n equals 0 to x of x to the nth power. X is between -1 and 1. Find the power series and interval of convergence by differentiating the given power series. Our function is f of x equals 1 over 1 minus x squared. All right, so basically what we're going to do is take the derivative of the series that we're given to try to find the series that we have here. So let's do it. First, let's take a look at what the derivative of our original function was. You can use the quotient rule. I personally would rewrite this as 1 minus x to the -1 and use the chain rule. -1, 1 minus x to the -2 power. Chain rule says times the derivative of the inside. So we pick up a -1, times the first negative makes it positive, and then rewrite the negative exponent accordingly. All right, so if you notice, the derivative of our first function is our second function. In other words, the derivative of this guy is that guy. So we did this move, which means when we take the derivative of this series, we'll get that series. So now that we verify that the derivative of the function we have is the function that we want, let's set up the original function. 1 over 1 minus x is equal to the sum of n equals 0 to infinity of x to the n. And just for kicks, I'm going to expand this. 1 plus x squared plus x cubed plus ... And now let's differentiate both sides with respect to x. We've already shown that the derivative of 1 over 1 minus x is 1 over 1 minus x squared. And now all we have to do is take the derivative of the sum. The derivative of x to the n, just bring down the power and subtract 1. N times x to the n minus 1. If we took the derivatives over here, the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x cubed is 3x squared, plus etc. And let's make sure that our expanded version matches our original. Our sum, excuse me. If we put n equals 0 here, we get 0 times x to the -1. Well, 0 times anything is 0, so we're okay there. If we put in 1, we get 1 times x to the 0, which is x. If we put in 2, we get 2 times x to the first, so everything seems to be okay. Now, is it necessary to write that 0? It is not. So we could get rid of the 0 and we'd be perfectly okay. But where's that represented in the sum? Notice that when n equals 0, that's what gave us the 0 term that we could ignore. When you take derivatives, sometimes you are redundant in writing things that you don't need to. In this case, writing n equals 0, because n equals 0 gives us the 0 term, and who needs a 0 term? So as a consequence of that, we could say that since n equals 0 makes nx to the n minus 1 equal to 0, we can start the sum at n equals 1. Therefore, our function, 1 over 1 minus x squared, we can actually, excuse me, it's not right. The quantity 1 minus x all squared is equal to the sum n equals 1 to infinity of n x to the n minus 1. Is it necessary to get rid of that extra term? Not really, but just know that you can. But we're not out of the woods yet, because now we need to know the interval of convergence. Our theorem from the previous video says this converges on the same interval that we saw that we had before we took the derivative. In other words, we get the same convergence as we do right here. But when you take the derivative or antiderivative, you may pick up convergence on the endpoints. So we still have to check x equals -1 and x equals 1 for convergence. So let's check x equals 1. When we put 1 into our new function, we get n times 1 to the n minus 1, but 1 to any power is just 1. Well, it should be pretty clear that this diverges. The nth term does not go to 0. So this is a quick diverges. And we also have to check -1. And if we put -1 back into our series, we get n times -1 to the n minus 1. This is an alternating series, but notice that without the alternator, it still blows up. So this diverges by what I once dubbed infinite oscillation. So that means that when we said 1 over 1 minus x in parentheses squared is equal to the sum n equals 1 to infinity of n times x to the n minus 1, when we said it converges on the open interval -1 to 1, we were correct the first time. We didn't know, and we weren't wrong before. What we said was true. We just don't know if it was complete because we hadn't checked the endpoints yet. But it does converge on the endpoints. I do want to show you one more thing real quick. And again, this isn't super necessary, but depending upon where you go after this class, especially if you're going to engineering and physics, you may run across some professors who are more nitpicky about these things. Can we make this a single letter? Yes, we can. We can do a substitution. We can say n minus 1 equals k, which means n is equal to k plus 1. We'll need that here. And n equals 1 implies that k equals 0. N equals infinity implies that k is equal to infinity. So we could write this as the sum k equals 0 to infinity of k plus 1 times x to the k, if you get one of those professors that insist that you have a k there and not an n minus 1 or something like that. I think the series in black right above it is perfectly acceptable, but you can make a substitution so that you can get the power to match the index in this particular case.